Okay, so good afternoon, everybody, and welcome to this online workshop of Laser4MaaS to discuss about laser production as a service. My name is Antonio Castello. I'm technology manager at EPIC. We are part of this European project Laser4MaaS in the task of dissemination and communication. It's a pleasure to have you all here to know more about the project and also the latest advancements. Just a few words about the project. So Lasers4MaaS is a EU project that have several goals. First is exploring the benefits of laser welding using dynamic beam shaping for the tasks demanded by several industries. Also the use of AI tools to optimize the processes, and also the digitalization with development of tools which can allow the servitization of the process. And at this moment, we are in the month 18 of the project, and it's great to have you all here in the room to talk about the latest advancement and also to inform about what is the status now of the project. So we pass to the agenda now. So this is the topics that we will discuss today. We will start with the project introduction, but our PI, Pasquale Franciosa, he's the head of the laser welding group of the WMG in the UK. We will also have a presentation by King Landman in Stuttgart University about the process optimization work. We will continue with Christoph Nutzel, the CTO of the company Futurize. That he will talk about the Laser4MaaS platform and the database, and we will finish with the application, an example of the use case, with a presentation by Jao Ren, Principal Research Engineer at the UK Atomic Energy Authority. So as discussed, it's a pleasure to have you all, and we will have time for questions after this presentation. So for the moment, it's a pleasure to introduce you all our PI, Pasquale, head of the laser beam welding at WMG. So Pasquale, you can start sharing your screen and you can tell us a little bit about the project and the status nowadays.
Yes, yeah, absolutely, Antonio. Thanks. So welcome everyone. So I think I can start sharing first. Do you see my screen, Antonio?
We see the screen, now the slides, and probably now it's in presentation mode.
Presentation mode. Okay, perfect. So maybe right. Yeah. So thanks again, Antonio, for the introduction to the project, to the agenda as well. So yeah, so I will cover the high level view of the project. So where we are coming from, what we have in mind as objective and targets for the project. And then I will present some of the latest results we got on one of the use cases we have within the automotive sector. So we're talking about battery coolers. So let's start from the beginning. So where do we stand overall in terms of production? Yeah, so we talk about laser as a service for production, but let's start talking about production systems. I'm pretty sure this is what I have on the slide is pretty familiar to most of the people. So over time, yeah, we've been going through different phases of industrial, we call revolutions. So starting from the first industrial revolution up to Industry 3 with the PLC, automation and robotics. And then in 2010, we had the new step, so a new transition in Industry 4. So we call Industry 4 or Fourth Industrial Revolution, where we introduce digital technologies within the production systems, together with the smart sensor, IoT devices, and AI, yeah, with all the machine learning and all the AI technologies. So the trend is really going from manual operations to more automated or even autonomous systems. This is happening these days. And then we had the idea of introducing like a new approach that we call manufacturing as a service. So the question we have is manufacturing as a service the next frontier within the production systems? We don't know. We will see in the next probably next few years. But our definition of manufacturing as a service is basically saying is to produce on demand customized products with high quality, flexibility, and short lead time. So if you see, yeah, we basically have all the main, let's say, elements: time, quality, cost, yeah, with the customization, and then on demand. Yeah, so on demand is what's happening already since few years. So end users wants to have not only one product but customized products depending on the specific requirements and expectations. So we want to bring all those elements under the same roof as a manufacturing as a service. Now, to put in context, we are working within the high-value laser welding industry. So all the technologies we are developing are related for the laser welding industry. Some of the technologies can be exploited outside of the laser welding industry because they are more horizontal, but now specifically within Lasers4MaaS, we are focusing to the laser welding industry. Why is that? Because again, the end user wants to get the right quality on time at the right or reasonable cost, and on top of it, we want to meet the sustainability target. So the current challenges with any, I would say, laser material processing technology is probably around the cost. So usually they are high capex intense. So there is an acceptance challenge. Controllability. So laser technologies are in general not so easy to control because there are many parameters that must be controlled. Reconfigurability. Yeah, it's not only about changing power and speed, it's also about the tooling, automation, jigging, welding sequence, and few other, element of flexibility. And certification. Yeah, certification is usually very well underplayed. So people are ignoring certification, especially in in research environments. But these days, certification is becoming even more crucial. So starting from data sharing and interoperability. So those are the four macro we call grand challenges. And those are exactly the challenges we are trying to address in the project. So all in all, yeah, this is how we are developing the project. So we are bridging, let's say, the left-hand side, which is like the classical way of developing laser technologies today. So it's like laser production is a tool. So we go through laser to material interaction, we go to laser sources, optics, welding heads, all the metallurgy of the weld, optimization, sensors, and process control. So this is like the typical loop we do, every day when we develop a new process. And we want to bridge this laser as a tool with the laser as a service. So we're bringing other ingredients, and we find the synergy between those additional elements. And those elements are about reconfigurability, digital platform, digital services, circularity, sustainability, interoperability, and yeah, on top of anything else is the AI-based decision support, with Kim will present just after my introduction slide. So where do we stand with an end user perspective? So if you are end user and you want to use like the technology, so the first question is, okay, to me is about quality, time, and cost while achieving my sustainability targets. Okay, so we go to the marketplace. There are different vendors, different suppliers with different capability. I can pick the one which is more relevant to me. Okay, and then the job shop manager on the other end will say, okay, great, we got to the job, but now I have to optimize the process to deliver the right quality on time at the right cost with right sustainability targets. So for the people working in the laser welding industry, the first question that is asked, okay, but what's the laser system that is supposed to be used for the job? Okay, what's the clamping? Are we going to use a shielding gas? Are we going to use filler wire? And the list can be very long. Yeah, beam shaping, wobbling, type of joints, plume management, yeah, prep of the sample. How do we assess the quality, testing requirements, maintenance? This is a very, very dense, cloud. This list can be very long. So there is complexity there. Okay. And we want to address this complexity in selecting the parameters, selecting the equipment, reconfiguring the system, assisting with the data management, with the monitoring, with the maintenance. How we do this? Yeah, we do by combining the manufacturing technologies, which you see here in the list, with the digital services, which you see on the right-hand side. So manufacturing technologies, yeah, as you can see, is diversified. The core technology is the dynamic beam shaping, which I will show some slide with some result in the next, let's say, 1 or 2 minutes. But we also have, modular fixture, modular production, and IoT devices. And then we have a list of services. The list is quite long. So today we only cover the process optimizer. So Kim will be presenting it. And then Christophe from Futurize will be presenting the overall structure, the overall philosophy around the services and the digital platform. And then Yao will be presenting some results about the use of dynamic beam shaping for welding thick section in the nuclear fusion industry. And then I will add also some slide in the very end about high-speed welding for battery cooler using dynamic beam shaping. So the project is a consortium. We have 11 partners distributed between UK and Europe, with Israel as part of it, with the Sivan Lasers. So yeah, we have people in partners in Italy, in France, in Germany, Austria, the Netherlands, and then UK. So it's a very multinational consortium. We are open to expand our advisory board. We have currently already 6 members from different industries, including a couple of end users. Yeah, and we are open to expand our advisory board members, yeah, because we want to really see different point of view from different industries and different end users. So if you want to know more, please let me know, or let Antonio Castello from Epic know. Yeah, and then we can engage in conversation. Next slide. Yeah. So yeah, I want to quickly show also this slide because sometimes I have seen confusion from some people. So what we do and what we don't. So we are not trying to develop a digital platform for connecting buyers and suppliers. Yeah, this is out of scope because there are already solutions available. On the internet, on the market. We are not managing suppliers, and we're not managing quotations and logistics. Okay, so this is totally off from our scope. But what we do, or what at least we are trying to do, is across those 6 objectives. So reconfigure, connect with the digital platform, control using sensors, digital twin, and AI-based control systems, predictions using high-fidelity modeling and reduced order modeling, improve using dynamic beam shaping to solve challenges in typical welding jobs, like welding high speed, thick sections, dissimilar materials, including tin foils. Yeah, so we are trying to solve well-known challenges using the technologies we are putting together in this project, and then comply. So all the certification, including the digital product passport, which on some products, including battery packs, is becoming pretty much policy from the EU. So any product, any battery pack must include the DPP, which is not clear yet what should be included. And the project is also contributing in shaping the digital product passport for the key products moving forward. Yeah, so application and end users are also diversified. You can see the list. So we have use cases within automotive, e-mobility, so the battery cooler. We have a food packaging. We have renewable energy, and in particular, we have the nuclear fusion. So what Yao will be presenting after me. Application in aerospace, and also application in the pharma industry. So very diversified. Yeah, you can see some of the target KPIs, how we want to measure it across the 6 objective areas. Now, just very quickly, I want to show you one of those applications in the automotive sector. So this is the mock-up of the battery cooler. This is pretty interesting application because currently the way how this is joined together is in brazing in furnace. And as you can expect, being a furnace operation is very high energy intense. And this also is a relatively slow process. So that is our benchmarking. So we want to replace the brazing with the laser welding operation. And in order to meet the cycle time, we have to weld at least 400 millimeters per second as a bare minimum, with a target value of 800 millimeters per second. So that is very challenging because with high speed welding on aluminum, when you cross 200 or even 300, let's say, is a threshold 300 millimeter per second, you start getting this humping profile, which is a defect on its own. You have undercuts, you have a stress concentration, we have porosity. Yeah, you are losing penetration, and I mean, it's basically an unstable weld. So that is a problem with this application, and this is where dynamic beam shaping comes into the play. So we have done extensive testing using different beam shaping profiles. So this is one. This we call single click profile. So okay, let me start the video again. Oops, there is a delay. Let's try again. Sorry, I think. Oh yeah. Yeah, right. Yeah, so this shape we call single click. You basically have a central high intensity spot in the center, and then there are 4 small lobes on the sides. Yeah, you can see what I'm marking now on the screen. And because of that, yeah, you get a pretty nice weld profile even at 600 millimeter per second. And you can literally see from high-speed video, yeah, the side lobes that are making the molten pool a bit wider in the transversal direction, and this is helping in reducing the high-speed jet from the molten pool. So pretty stable weld. As a comparison, yeah, we tested different beam intensity profile. So this is the next, if again the video is assisting me today. Yeah, so oops, too fast. Yeah, so this is the next one. So here we have 2 dots, top and bottom. And again, the same speed power has been adjusted, and you can see now how this is becoming unstable. So it's not a very good beam intensity. Another option is to use 3 spots, 1 in front and 2 behind, because theoretically and conceptually, with 3 spots, you are enlarging the molten pool in the lateral direction. But in this case, yes, we don't get a stable pool. Yeah, it's very unstable. There is like a massive concavity with 2 massive humps in the weld profile. So not very stable process. Yeah, and this is how it looks like if you start comparing the 2 cases. So the major difference between these 2 profiles is the way how the molten pool is evolving. With a single click, the molten pool is more enlarged in the lateral direction, and the velocity field going backward is reduced. So this is helping in stabilizing the process. With the 2 spots, yeah, that doesn't happen. It's more unstable, it's more aggressive. So there is more, let's say, backward flow jets, which makes the pool unstable and then more prone to humping formation. We also did a comparison against a standard Gaussian beam. So left-hand side is the single click from the dynamic beam shaping. The right-hand side is the same process, yeah, the same speed and comparable power, but using only Gaussian beam, so no side lobes, and only from the high-speed video you can see the difference in terms of process stability. So this conclusion, I mean, is very clear. There is a chance of optimizing the process, optimizing the molten pool, tailoring the molten pool to improve, the performance in the end. The fundamental question is, okay, we have all this flexibility, but how do we choose the right beam shape for a given manufacturing KPIs? And this is exactly what Kim will be addressing in the next presentation. So thanks for listening. Hopefully we still have time for questions. And I want to repeat myself again. We are open to expand our advisory board if you have any interest and if you want to be engaged. We meet every 6 months. So we have meetings with advisory board every 6 months. The next meeting is going to be in September, towards the end of September. We are happy to add, more end users and new people to the board. So again, please let me know or drop me a message or let Antonio know if you want to be part of it. Thank you.
Thank you very much, Pasquale. So we have time for questions. If there is any in the room, you can raise your hand and make your question directly to Pasquale. I have perhaps a question about the challenges of playing with so many options in dynamic beam shaping. You showed in the use cases that you were trying different configurations. how challenging can be at the moment of defining the best configuration for one particular task, and how simulations can perhaps support this decision.
Yeah, so I would say challenging is let's put this way. So it's very flexible. So on the plus side, you have enough flexibility. So from the same laser source, yeah, you can generate theoretically like unlimited number of beam profiles. So very flexible, but that is also adding the complexity because you don't know where to start with the selection. So the way how we are tackling the challenge, yeah, is a combination of obviously, experiments, because we have to keep developing the process. We have to understand how the laser is interacting with the material, so laser to material interaction. But also is all the modeling, so the high fidelity modeling, so the multi-physical modeling of it. The challenge with the multi-physical modeling alone is the computational time. So multi-physical modeling, when you start building together heat transfer with the phase change, going to keyhole modes, modeling also the multi-reflections within the molten pool, plus modeling the dynamics of the beam itself, yeah, is adding computational complexity. So solution to that is to use reduced order modeling, together with AI decision support. And this is somehow what Kim will be presenting in the next meeting. She's not touching exactly on the multi-physical modeling and reduced order modeling. She's discussing the part on the AI decision support for helping in selecting the beam shape profile for a given list of KPIs.
Very good. We have also a question from Anand. You can unmute yourself.
Hi, Pascal. It's a very nice presentation, nice work. Just have a very quick question. Like we are using the dynamic beam shape to stabilize the keyhole at a very high welding speed, right?
Yeah.
Have you checked the effect of a beam oscillation on stabilizing the at very high speed, or it is not possible?
Yeah. There's the thing. Yes, I mean we have that actually is our starting point, is our baseline. So the beam oscillation or the beam wobbling is okay, but with the beam wobbling you can work around the kilohertz, because the wobbling, with the galvo scanner you are around the kilohertz scale, and with the kilohertz you can't go faster than 200 millimeter per second welding speed. So if you want to go much faster, yeah, we have to add other dynamics, and the wobbling, the classical wobbling technology is simply not fast enough. Yeah, it's not fast enough to cope with actual high speed of the laser beam itself. So that's why we are saying, okay, we want to jump from kilohertz wobbling to megahertz using this technology with dynamic beam shaping. So obviously, I mean, today is only a few minutes. I didn't have time to show other results. We have also done a quite comprehensive study on understanding the impact of the frequency of the beam itself, because again, it's dynamic. So the beam can go anywhere from few like 100 hertz up to megahertz. So we did a comprehensive study to understand how the frequency of the beam itself is stabilizing or even making the process more unstable, because with some frequency range, you are like almost in the resonance with the molten pool. Yeah, and that is creating even more instability. So we have studied, the effect for a couple of beam shapes on a different frequency regime, the effect on the keyhole dynamics. And yeah, I mean, results are quite interesting. And I mean, we are publishing something now, so we should have a publication, I mean, in the next couple of months. So once it's done, I will send you the link.
Yeah, thank you.
Yeah, thanks.
Another question from Jesus. Thank you, Anand.
Hello. Hi, Pasquale.
Hi.
Okay, very interesting presentation. So one question related to the high-speed welding. Do you need to use shielding gas in this?
That's a very good question. It's a very good question. So let's say again, it's a baseline, because we know what's happening in the from other people, from other companies, including other laser vendors and other machine builders. So those plates, those are aluminum 57 and 54. Yeah, some people I know are using nitrogen as a shielding gas. However, the welding speed is in the range of 150 to 200 millimeter per second, which is okay, because you can put a shielding gas nozzle attached on the end effect, I mean, on the robot, and you can move the nozzle around. the problem, if you start going much faster, and we want to go up to, I mean, more than 600, even 800 millimeter per second, and using shielding gas becomes a bit too complicated. So at this moment, yeah, the video I've presented with these results, we are not using shielding gas. So we are trying to weld without shielding gas. So fully autogenous.
Okay, thank you.
Yeah. Okay, thank you, Jesus. So I think, thank you, Pasquale. We can move now to the next speaker. And as Pasquale mentioned, we will have now a presentation in process optimization. So it's a pleasure to have here Kim Gluman. She is a researcher at the University of Stuttgart, EFSW. And Kim, you can start sharing your screen and the floor is yours.
Thank you. I hope you see my screen now.
We see the screen, yes.
Perfectly. So thanks, Antonio, and thanks, Pasquale, for the nice introduction. I'm here today as a representative of the University of Stuttgart, and together with my colleagues, Michael, Volker, and Professor Michalowski, we are currently developing, as Pasquale already mentioned, the process optimizer, so the AI-driven decision support in the project. And today I'll give you a small overview on what we've already done. Let's see if that, no, I actually have to deactivate the laser pointer. Okay, so our understanding of the process optimizer is that it is a digital service that supports the user in identifying suitable combinations of process parameters in order to achieve user-defined KPIs. A little bit of that Pasquale already mentioned in his presentation. So KPIs from a view of, for example, two applications engineers could be a higher productivity, less production costs, or even only, which is mostly the most relevant one, the quality. So in terms of laser welding, that could be, for example, dimensional accuracy, so depth or width of a weld seam, the occurrence of defects or to avoid them, such as humps, undercuts, cracks, pores, depth fluctuations, or spatter, or something completely else, mechanical integrity, or the aesthetic appearance of a weld seam, if you can see it. And as probably most of you know, we have quite a lot of influencing factors on one hand on the productivity and the cost of the weld seam, but of course also on the quality. For example, the laser power, the welding speed, the focus diameter, intensity distribution, and many, many more. And in the Lasers4MaaS project, as Pasquale already also said, we are working with dynamic beam shaping, so we add even more parameters to that already large parameter space. Okay, so normally we tackle that problem on which parameter to choose in order to obtain the weld seam we want to have by performing quite a lot of experiments. This is cost and time intensive, and we want to reduce the effort normally. Mostly we do that by prior knowledge. So either we are already quite the experienced application engineer, maybe with years and tons of experience, and we've performed already thousands of weld seams, and we know exactly how the weld seam behaves in dependence of the parameters. Or maybe we have a look into Google Scholar or whatever on publications, what other groups published about process parameters and the results. Or maybe we just ask colleagues or we use simulations, whatever. And thereby we can already reduce the effort. I think that's common knowledge. And in Lasers4MaaS project, or also lately, machine learning approaches gain interest in order to reduce the process development times and also the effort we need to find optimal solutions. And yeah, okay, sorry, that was, okay. So thereby we want to provide optimization as a service for manufacturing. We want to include user-defined objectives and process constraints. So having the adaptable setup Pasquale mentioned. We want to provide AI-driven proposals of optimal process parameter sets by including iterative and experimental evaluation with a continuous model updating. And we want to have a system or an optimizer that requires minimal prior process specific expertise from the user. So if you are already, if you have prior knowledge, it's good, but it shouldn't be a problem if you do not have any prior knowledge. And the value for manufacturing as a service is thereby that we have rapid and robust process setup, ideally, that we have a scalable and transferable process knowledge, a consistent process performance across jobs, or that we can adjust the parameters easily and fast, and thereby reduce the trial and error, scrap, and setup effort. All right, so that's about the scope. And how do we actually implement that? I'll show you now. We're using Bayesian optimization. Colleagues of mine and probably quite a lot of other groups now showed and thereby demonstrated that surrogate-based optimization, and in particular Bayesian optimization with Gaussian processes, are really good for identifying process parameter in order to fulfill predefined targets and to efficiently optimize black box processes, so where we don't know the exact behavior. Therefore, okay, it works really well with low dimensional parameter space, so no more than 15 to 20 parameters. The less actually is the better, because the less parameters we want to optimize, the less experiments we have to do in order to get suitable results. But the really nice thing about Bayesian optimization with Gaussian processes is also that it can handle noisy data. And everyone who works with process monitoring knows how noisy data can be that we monitor. Okay, one difficulty is that we often have several quality metrics, for example, the quality and the production time, and which need to be considered simultaneously, and their objectives may partly conflict with one another. So let's assume that with increasing welding speed, so increasing productivity, the quality gets worse since we have more spatter. Just an idea. So sometimes the optimization objectives can conflict, and that actually is a problem for the Bayesian optimizer, or can be a problem for the Bayesian optimizer. We have to take into account. And one approach to tackle that is multi-objective Bayesian optimization. This one models several metrics as one. So it has one model for, let's assume, welding depth, one model for spatter, and so on. And then we can approximate the Pareto front and decide individually which set of parameter gives us the best compromise in order to have a certain welding depth, a certain productivity, and the least amount of spatter. But the approximation is data expensive, and thereby we lose a bit of the advantage the Bayesian optimizer normally gives us. And that's why most laser processes work scalarizes the response into one objective that has to be defined prior by the user. And that's one part of what we are working on in the project, how we can optimize, how we can automatically define the objective function. So just to give you a small overview, because not everyone probably has heard about the Bayesian optimizer, let's start with the experiment. So we performed one or several experiments at the beginning, and then we evaluate that. So we have a parameter set X, and we measure the criteria we want to achieve. Oh, that actually shouldn't be a F, it should be a Y. So for example, welding depth and spatter. We then have our predefined objective function, which maps the achieved quality type criteria to one scalar value. So that could be everything. It could be 1, it could be 10, whatever. It just maps the quality to one value. And based on these values, we can initiate and update later on a Gaussian process model. That's our surrogate model. We used to map the parameters we applied to our objective value, which is an indicator for the quality quality that was achieved. And we have a mean, so the best estimate, and the variance, so the model uncertainty. And based on this model, we thereby initiated the Bayesian optimizer, provides with an acquisition function that's just part of the optimizer, where to perform the next parameter. And thereby, we can drastically reduce the amount of experiments needed in order to find suitable process parameter. That is what those two papers, for example, show. Okay. So how does this look like in our platform scope? We have the user that interacts with the dashboard, which is developed by Futurize. And I think Christoph will tell you a little bit about that in a few minutes. Then we have the process selector, which is developed by the Technical University of Vienna. It's the auto-reduced model Pasquale already mentioned, and gives a first estimation of suitable power or promising parameter sets. This is returned to the user, who performs experiments, evaluates them, and then has two options. Normally, based on these first results, the user can iteratively optimize the experiment himself. So that will be a loop between the experiment and the evaluation. But in terms of our project scope, the idea is to return those evaluation results to the platform, which then leads to the process optimizer loop. The optimizer then suggests the next set of parameters, which is returned to the user. The user performs the experiments, evaluates it, and returns the results to the optimizer, which gets updated, and then the loop starts again. Okay, so let's zoom a bit into the loop itself. So we have a definition of the welding test, we have a parameter space, we have targets, which are called KPIs in this scope, and we have constraints, maybe a maximum amount of power or whatever. These are user-defined and provided by the platform. So then we have the initialization I mentioned earlier. So we have either first estimation by a technique called Sobel sequence, or based on the process selector that gives us a first set of parameters to be tested. The user performs these experiments, evaluates them. In this case, we use, for example, welding depth or seam elevation and undercuts, returns those values to the dashboard. The dashboard leads them to the optimizer. The optimizer evaluates the weld seam quality with the objective function. Then we have the scalar value C, and the Bayesian optimizer then initiates the Gaussian process based on the parameter set and the scalar value, and then suggests the next set of parameters. And then it starts again. Okay. This might sound a bit complicated, but actually it's really, really easy to use. I developed for testing reasons a small platform, and I want to show you on that how it could work. So we have here for the user to see the suggested set of parameters to test. So you see here we have already done a few iterations, optimization steps. Then the next one would be this one, and let's hope that this time the video works. Yeah, it looks good. So we then return the values we've measured. These are just fictive values right now, so they were not actually measured. Then we submit the results. You see with the sign here, up here that it updates, and then you get the next set of parameters to test, and you mark them against testing, and so on. So the interaction with the platform and the usability should be quite easy. You can then see, for example, how the individual parameter sets performed and what parameters were tested. So it's quite intuitive, I would say. We already performed first experimental campaigns with that. For example, here we optimized the laser power, the feed rate, and the shape. This is a CVAN specific, so don't wonder if you are not familiar with that. And we optimized to these parameters. And this is just the evaluation result. So we have in the blue colored diagrams the parameter and how they changed. The red ones are the KPIs. The green band is always the tolerance and which is tried to achieve, and the green stars are the best parameter combinations we had. Due to time, I will not go further into that. We just tell you that it was successful in our setup. So regarding those values and our targets we wanted to achieve, it was just a demonstration. And if you're further interested, I will dig a bit deeper into that at the lane. And there will also be a proceeding, so you can keep your eyes and ears open. Yes, and that was the small overview over the process selector. Thank you for your attention. If you have questions, yeah, I think we have time for questions. And otherwise, maybe I'll see you at the lane or at the Icaleo. There I will go a bit deeper into how to include complex beam shapes into Bayesian optimization. Thank you.
Thank you very much, Kim. So we have time for questions for Kim. I can perhaps have a basic question, and it's related with the when the process optimizer selects the best parameters for one task, would this also fit the initial tool developed by TUVM? So the next time one similar task is requested, the first parameter suggested will be somehow modified because some other experiments were already optimized in the past? Or there is no connection between this first parameter suggested and the optimizer?
There is a connection. So we initialize the process ideally with the auto-reduced models from TU Vienna. So we do not need that much experiments and thereby reduce the amount even more. If due to any reason the process selector service is not available or it does not fit our targets at all because, I don't know, there are constraints that are not taken into account for the model, for the high fidelity simulation modeling, then we can initialize the process by completely without any synthetic data or simulated data. But normally we are aiming to reduce the amount of experiments that have to be performed by using those simulations. Did that answer the question?
Yeah, definitely. We have another question also in the chat by Nicolas from Mora Classe. I don't know if Nicolas, if you can do the question directly. Are you connected, Nicolas? If not, I can read the question. How does your optimizer deal with the trade-offs between conflicting performance criteria? Will you elaborate on the multi-objective aspect?
No. So we aim to solve or to handle that best by having a good objective function. Of course, we always lose some information there, but we will not actually calculate the Pareto front or do multi-objective optimization due to the amount of experiments we would need, therefore.
Okay, so Nicolas, I hope the question was answered. If not, you can also write again in the chat. And I don't see any other questions. So thank you very much, Kim, for the nice presentation. And go to Lane and Icaleo to Kim's presentation to discuss more in detail about the work here. So we can move now to our next speaker. And as Pasquale also mentioned at the beginning, the next topic is the platform and the database. So it's a pleasure to have Christoph Nutzen, the CTO DAC of the company Futurize. So Christoph, the floor is yours.
Thank you, Antonio, and welcome everybody. I'm talking a little bit about the platform that connects all the parts, the optimizer, for example, that Kim just talked about. And yeah, I'm sharing, right? Yes, it says so.
Yes, everything good.
That's great. So welcome everybody. Welding systems were like are engineering zeros traditional. So now we're like also connecting with a platform that more to a service like Pasquale showed. So it's looking at the situation first from the problem statement that we're all trying to solve here, and also the platform really addresses, is the capital trap and the physicality trap gap. Meaning, so there is like the capital trap, like buying a laser, so on, can be very expensive. So you take all the burden of the risk of the financial investment onto it, and trying to leverage as well out of that, but you are dependent on your single kind of user being you. And the physicality gap, meaning like identical digital process configurations. Like if we have a disconnect between the processes, so every laser is slightly different. How do you evolve that? How can you really be laser as a service? How could you take one process to another laser in order to create a service business? And these are kind of two important parts that the platform tries to address overall, and using all the services being built and all the research being done by WMG and others. And when we are looking at from a strategic perspective, first of all, we're seeing this interoperability and architecture challenge as a three interoperability framework we needed to understand how can we abstract the different parts of the platform and database and all the surrounding services. So what we're seeing is here the micro level, the shop floor. We have different kind of shop floors around Europe or the world for one supplier, for example, and we want to connect them to the meso level, what we call the platform. The platform is, for example, where the optimizer that Kim just presented is being called. So this is where we're trying to create the trust between the different parties, between the different laser shop floors. And then we have on top of that the topic about macro level. That's the digital product passport decision frameworks in order to fulfill sustainability tickets, as also Pasquale just mentioned, as a key aspect of our work. So we proposed already this framework at the latest interoperability conference in Madeira, the IESA Madeira 26, where we presented this multi-level framework and are currently continue developing it. And what does it mean from the platform perspective? So it's a decoupled platform. So our way how we think about that, every part of the platform needs to be interoperable. We need to be able to change process selector, optimizers, and everything that's in there. So what we have here is like a core application that consists of an interface that Kim already mentioned. We are also having a platform database that allows us to store data, but also in their setup, how we did it, it protects IP rights against different competition. And we are already able to connect to the lasers and the shop floor in order to extract all the data in lifetime and also pushing data for processes. And when we're looking especially at the service side, we have the process optimizer that Kim just showed. We have the process selector that we're using, the sustainability and cost evaluator, and the process controller and code generator. And we're using all of them from our platform, like how Kim just showed it. And how we're defining from a platform perspective, an API schema against it that we're currently stabilizing in order to be able to also have other kind of services being plugged in that does the same thing or different things in order to be truly interoperable for the platform. And the key concepts are here, the process selector and the optimizer, leveraging the machine learning and the Bayesian optimization that we talked about. Then the process controller code generation outputs like flashing ready C code that dynamically adapts variables mid-weld, so that we are really also can take on the real-world variances better and adapt fast. And the sustainability and cost evaluator, which is done by Uni Leiden, allows us to compare between different sites, different energy consumption, different energy mix, different kind of ways how material is getting shipped to a site. And when we're now talking more about the data side, because a lot of the problems are in trust and IP rights, so nobody wants to give away their secret sauce how to do that, we needed to find a way in the platform to separate about that. So, for example, database, we're using a PostgreSQL. It's a relational schema designed for multi-tenancy, meaning every kind of player, every kind of company is being filtered and protected from each other to that data is leaking out from their IP. So we are having a ensuring the trade secret of the IP, and we are actually trying to ensure that this is being then also able to move to clients on site as a database. At the moment, we are working still centralistic in order to stabilize the database schema and the APIs, but overall in the future we will be able to move databases directly to the client and still being able to use a global platform. And on the other side is how do we ingest the information into the platform. We're using a Nets chat stream telemetry, which allows you with a lightweight broker to ingest the data from the laser. So you're have remote monitoring, you have always understanding about the health of lasers in order to know, can I use a laser, which conditions it is, and also understanding the data from a weld in order to understand the quality and also being able to react and so on, and creating the digital product passport out of that. Also in the setup, in comparison to maybe a blockchain technology that we also looked at it gives us a better way to integrate into federated spaces like the Catena X or the Manufacturing X world. Yes. But this is only the integral part you don't see. But what we also saw is a very key part of our work is like the cutting edge technologies. So meaning, how could we use the services of remote monitoring, assistance, and generative AI included in the platform? Because if you just can control it in an abstract way, how do you resolve problems when your laser has a problem? How could you call somebody from the laser provider, in our case C1, in order to help you to fix problems with your lasers? And also, we saw the complexity of configuring these processes and making the production life cycle of the laser welding working. We see also the benefits of generative AI, helping users to generate faster the required set of parameters, because what you've seen also from Kim is a lot of data is being needed in order to do the process optimization. How do you can fast track that? How could you be faster in doing so? And also for us, very key as Futurize is not just technical implementation, it's also the user experience. So we're really thinking about the user experience. So GenAI is also a way to do that in a more streamlined way. And also we're looking here not at the hyperscaler and the frontier model provider like OpenAI. We are really on purpose using Mistral AI as also with our EU consortium perspective is a key parameter. And as you see in the image on the right, you're seeing the current implementation of the AI remote assistant, where you can basically start a call with an expert in order to fix problems. And you can see slightly here a red arrow in the image. It's very light, but it's also a way to collaborate on that. And what kind of metrics are we want to create with such a platform, which you can see on the side, very easy, minimalistic user interaction with an AR technology to be really combining the physical and the digital world. We are looking at 4 key KPIs from our perspective. So the onboarding should be fast, that you're part of the network. The transactional success should be 100%. The remote anomaly resolution should be increasing. We are looking at the moment at the baseline of 5%, where we want to increase it above 20%. And the defect detection latency, meaning how fast can you resolve that, is like should go into sub-seconds, as you saw with all the services we are integrating. And we need to be candid here. We are also currently in active development phase. So this is why I don't have anything working that I can show, because we're currently integrating all these services into the platform. And then when this is like happening, and maybe in the next kind of webinar, we can show more really the interaction between services and the lasers, how this works together, because this is why it here is a little bit more abstract. But we are also looking at sovereignty, and in this case, true European digital sovereignty. So we decided to go not with the known hyperscalers out of the US. We went with a stack that is completely open source using Django and Python as a technology stack with React. These are very much well-known open source technologies. And we are using Scaleway, a French cloud provider, which provides everything what we need here. We are also not connected to them in any sense because we're using Kubernetes as a way to move the application from A to B without any big overhead. And we are also creating, like I said, the data isolation by design, as I mentioned already with the database. So we're really trying to be on the infrastructure and on the software application, really sovereignty and offering sovereignty to our clients and consumers, meaning they should be the owner of their data, process, and IP secrets, and protecting that is very key for us as well. And what's the conclusion, the outlook? So the roadmap ahead is, like I said, moving away from the standalone machine optimization to an industrial grid. If you really have a stable processes, how can you move them along a grid? My example is always, let's see, like it's October in Helsinki, and you produce something there, and you start to have less and less sunlight. How can you move a process to Spain where there is still more sunlight, where you can dynamically shift your production? It also connects very well to the Draghi report that makes now production decisions more energy strategies and more resilient in the supply chain area. And also, how could we, as said, the capacity routing, how could you deal with more demand than you expected? How can you move it to a different location in order to deal with that? And that's a very quick run through the platform in order to stay also a little bit in the time. And thank you for the attention, and happy to answer any question.
Thank you very much, Christoph. So we have again time for questions from the audience. I could perhaps start with a more general question about the main challenges of having this kind of platform for a type of process with so many different parameters, and now with the dynamic shape being even more flexible. So how is for you, how do you see the main challenges here in developing a platform, and the flexibility for future later processes, application of a similar concept to other potential processes like cutting or perhaps additive manufacturing even?
I think it's a data topic, meaning when we are at the point where we have more and more processes in the database and can help people to guide faster through which parameters is needed, it helps to speed up the process. But when we're starting from zero and there was nobody using the platform, it's quite of an overhead. Therefore, we are approaching that by the academics, helping to pre-fill the database, pre-fill that we are able to use AI actually to select. And it's not automatic selecting and you don't know, you use a black box, but helping you to guide very dynamically with AI through that. And also not just black box AI you may know from ChatGPT, but more of an explainable AI, which also gives you reasoning for certain aspects.
Any other question or comment from the audience? So I don't see anything. So thank you very much, Christoph. And I hope to see more details in the next workshops that you mentioned, that they will be more advanced.
Yeah, we are just integrating right now, and then I can show you a click dummy, but I think that's also quite non-descriptive.
Yeah, we will see. We will see more in the future. Thank you, Christoph. And we can move to the last presentation today. So the example of the use case, and as Pasquale mentioned at the beginning, is an application to a SIG section in the atomic energy kind of use case. And we have Yao Ren, principal research at the UK Atomic Energy Authority, and she's going to present the work in this field. So Yao, the floor is yours, and thank you very much for your work here.
Thank you. Can you see my screen?
Yeah, everything good.
Excellent. Okay. I think we're a little bit overrun. Do we still have time? We do, right?
Yeah. You can go with the presentation.
Sure. Okay. My name is Yao. I work at UK Atomic Energy Authority. I am a research engineer. So today I'm going to give some update on the work we have been carried out in Lasers4MaaS. The main development actually focused on the process development of our use case, which is a thick section, especially for thick water pipe welding for nuclear application. And I would like to acknowledge the contribution from Shahid and Pasquale, because basically the welding trials carried out at WMG. So here, I'm working at RACE, which we branded as a remote application in a challenging environment. We are actually remote handling and a robotic division at UKAEA. At RACE, we design, we build, and we test robotics, mainly used for challenging environment, including space and including petrochemical and other area, but mainly we're actually doing work for nuclear fusion. When we talk about challenging environment regarding nuclear fusion, that refers to high temperature radiation, narrow space, and also hazardous materials and magnetic field. Sometimes it is also vacuum pressure. So what we do here is we try to carry out maintenance work for the tokamaks, which we have to use robots because the environment really doesn't allow human beings to access. And yeah, we can straight jump into pipeworks. Why pipeworks quite important? Because pipeworks is a very important support system in the tokamak. When the plasma operation is actually happening, it generates a lot of heat. So the plasma facing components are required to be actively cooled by some coolant. I think the most use of the coolant is water, especially when we go back to jet time, which is a joint torus, European torus based at our side. It was designed for using water to actually cool the tokamak. And because of this, we have to have a lot of pipe systems actually deliver the coolant. On top of that, pipe system also deliver a fusion fuel. For example, if it's lithium lead or some other potential fuel to actually regenerate the energy to generate plasma. And there are loads of pipes. If we want to think about it, probably hundreds of them. They are connected to the plasma fissing component, and every now and then, for example, for EU demo, the plan is to actually replace those plasma fissing components every 5 years. The work needed is to actually disconnect the pipes from plasma fissing component, take the blanket out, because blankets basically are sliced into probably 20-30 pieces that will be lifted from the upper port, and they will replaced with a new component with segments of the pipes, and then that will be rejoined. The most identified method to reconnect the pipes is through fusion welding. Back then, for jet, a lot of pipes, they are actually welded using the traditional TIG welding. And for EU demo, my colleagues, they have explored using laser as a solution to either cut the pipe and re-weld the pipe. So if we simply look at it, this is an image of the design of the pipe modules actually from the upper port. We could see different dimensions of the pipe, and also they have different thicknesses. This is a temporary module. That means these pipes needs to be disconnected through these lines, like those purple area. On the right-hand side, those gray area, they're actually the permanent pipes. So smallest pipe are featured with a 90 millimeter diameter, and the pipe wall thickness is around 5 to 6. And the largest pipe is about 220 diameter, which is the inner diameter with the pipe wall thickness about 16 millimeter. When we see these pipe modules is really clustered, there's no space actually to carry out any work from the outside, which requires all the cutting and the rewelding to be carried out from the inside. That's why they came up with a solution, develop a laser in-bore welding and the cutting tool a few years ago. I will explain a bit more. So when we look at all the pipes, actually it counts for 40% of the total upper port maintenance duration. That means during the operation downtime, quite significant amount of time we'll focus on the pipe cutting and the welding activities. And you know, for maintaining TOCMAC time and money, which is quite critical because you know, regarding the high radiation, any tool or robots or any system sent into that environment, if it's under high radioactivity, it might just die quickly. So time is money and safety is money, everything is money, and we want to do it efficiently, effectively, and economically. And I'm going to share these two videos. Just have a look.
There is no sound, Yao. I'm not sure if this is the one that you needed the sound.
Oh, there's no sound.
No, we only see the video, but not the audio.
Do you want me to do it again or?
It depends if you're.
Pardon?
If you think it is relevant, you can do it again. If not, we can continue.
Yeah, I think let's continue. I can just
Okay.
verbally introduce. This is a system actually my colleague developed a few years back. The idea was to develop this system, actually deploy the welding tool in situ. You could see actually the sorry, this is right. Somehow I missed it.
We are again
Am I
at the
stuck?
beginning.
Yeah, I'm stuck now. Sorry. Yeah, I think I just introduced this system, which my colleague developed this tool, and they carried out some feasibility study, which mainly focused on the thin material because of the power challenge. You know, compact everything into a small tool, and which to allow the tool insert into a pipe with 90 millimeter, the laser power was really limited up to about 2.4 to 3 kilowatt, and we managed to weld through 3 millimeter wall thickness within about 25 seconds. However, there were still some challenges. For example, when the power shooted up, the bending mirror got actually damaged because of the heating, because of the heat generated, and also there might be some design issue as well. However, the concept was proved. The process parameter was not really optimized. On the other hand, we also carried out some other work, try to test the laser power, like to identify how the laser power in we are needing to actually penetrate to a certain pipe wall thickness. We did some trials at other suppliers' sites, and we actually found out 10 kilowatts also quite struggle to penetrate about 10 millimeter using a multi-mode laser. If we wanted, we actually could use a combined hybrid solution, which means we use laser and the TIG together to introduce more heat and produce a multi-pass solution, which could actually make the joint up to 10 or even 20 millimeter. However, this is not the solution we wanted, because considering we want to deploy the system into really confined space, carrying all the packages like TIG source and laser beam, as well as some filler material, it's very difficult to control the processes. and it's very challenging to make sure we will achieve the beam quality if we want to operate remotely. So the objective in Lasers4MaaS, because using C-band laser, which is having the advantage of welding through thick material, but using relative low power, which we have seen references before, we would like to see if we could actually implement the solution to our thick wall pipe, and if we could actually join it reliably and efficiently. And further beyond to this point, we'd hope to develop an inboard laser tool for thick section, potentially can weld through using smaller power. That means the challenges on optic system will be reduced, or let's say the risk of delivering such high power will be reduced. And another thing is we wanted to develop robust welding process parameters that allow us to repeat the welding in a confined environment without damaging the tool. So this is the system actually set up at WMG we've used for our welding trials. We are using a C-band 14 kilowatts laser to deliver the beam through a C-band optical scanner. And also we have XY table paired with a system which allow our plates together with a jigging moving in the XY direction, and the Z direction can actually adjust the focus position. And this is slightly different from other system we used, traditionally, because it didn't come with some shielding and air blades combined, or let's say integrated into it. The first thing we tackled was to design and set up how we want to shield the molten pool and how we actually use the air blade to ablate in the plume generated during the process. Some initial studies actually give us some suggestions. It was found that a higher power together with air blade too close to the material surface actually induce high spatter and severe oxidation. And these are the comparison between how in the Z direction means actually in the vertical direction, how close and how far away we set up actually impact on the processes. And you can see the surface severely actually oxidized when it's too close. So after several trials, this is our final setup we used for process parameter development. We have the laser beam set up at a 6-degree inclination angle impinged at the material surface. And here, this is a tailored shielding gas set up together with the air blade integrated, which is mounted to the table. And during the welding, we are having the table moving with laser beam fixed. And for all the trials, we use a single click. The laser beam was at 133 micron diameter, which is really small. We tested different things to begin with, such as laser power, focus position, welding speed, and gas flow rate. We tested on the material at different thicknesses, including 3, 5, 10, and then we moved to 16 millimeter, which was our target. So some initial trials, probably some of you have seen this result. This is we have already disseminated. Basically, we could see a linear relationship between the laser power and the thickness we have achieved using their C-band laser. Actually, we achieved average about 650 watts per millimeter penetration compared to conventional multi-mode laser. Potentially, it was about 1 kilowatt per millimeter penetration, which actually represents a significant reduction of power, or with a significant increase of efficiency we would like to. So this is the baseline, and after that, we actually studied the shielding gas influence on materials. We compared the 3 different shielding gases, including argon, nitrogen, and helium. And we want to see if using different gases, we could actually achieve the same penetration less power. And on the other hand, oh, this is actually blocked my vision. And on the other hand, we also look at it, the spatter generated, the plume generated, oxidation as well. And another important thing is to study the porosity. If any gas type as a shielding gas could give us a good quality with less porosity. So here just share some of the welding profile. The welding matrix we generate here start with assume the power range based on our knowledge, and we'd like to compare the different gases at different power to achieve partial penetration towards full penetration with and without air blade. So the comparison is trying to see, okay, basically any impact from the gas gives us better outcome. This is a 3 millimeter we tested. We could see some of the pores generated, some of the cross-section actually look very clean, and we also can compare the penetration depth of each weld. This is 5 millimeter as well. Interestingly, we didn't achieve full penetration using the nitrogen gas. However, we achieved using argon and helium. And this is a 16 millimeter we have tested actually at a relative lower power, even at 8 or 9 kilowatts, we achieved a full penetration. So this is a graph just showing some comparison of the data we've generated. Some more generic finding is we find out power increase on increased penetration. The relationship is actually shows more higher influence on thinner material. You can see that actually the generation of the depths is more steep. And then we see actually on the 60 millimeter, basically for helium, it reached the full penetration actually at a fairly low power at 8-9. They will actually generate similar result. And in a fully penetrated weld, actually, we conclude that air blade had a negligible impact on penetration. I think probably it's just that when we set up, it was just about right, and the power or the parameters sort of fall into the sweet spot. And the shielding gas influence also is quite limited within the thinner welds, but becomes more prominent in the thicker section, especially actually for helium, which provides higher process efficiency. And we could see, that's as I already suggested, helium gives better penetration depth compared to the other two gas. And here, from the high-speed camera actually capture the spatter and plume generated. This is a really nice comparison. We can see with the increase of their thicknesses, we can see more spatters and we can see really strong plume generated. And if we compare vertically, we could see for thicker section, helium did give a really peaceful process compared to argon. That's really a nice result actually to compare the process. And this is a graph comparison actually, the number of spatters per frame generated. The quantification of spatter of the high-speed imaging actually shows us how their air blades and the shielding gas influence on the processes. Helium shielding welds produce a significantly less amount of spatter for all the material thicknesses. Nitrogen and argon were actually more comparable. And we believe that because helium atmosphere suppress plasma eruption more significantly and overall reduce the laser attenuation and improve the absorption of the energy. Also, as I said before, the penetration as well, because of the low attenuation, the penetration shows more effective using helium. This is another analysis. Is not fully completed. We've compared the shielding gas on the oxidation generation. Interestingly, we've seen at 5 millimeter fully penetrated weld, nitrogen did give a little bit high oxidation. which we don't know the reason yet. It's being investigated. Some hypotheses could be because hydrogen is not fully inert at higher temperature. Then if it's become a bit active, probably the performance of the shielding was not as great as, sorry about this, as suggested. And then, I'm sorry, this is not great.
That's okay, Yao.
Yeah. And yeah, but it is still unclear if it is welding process parameter related, or it is actually because some reason caused by the material manufacturing route, because we did identify some manufacturing routes of the material were different in the material we sourced. So we're waiting for some result from the 16mm results. And this is a porosity as well. Interestingly, we could see actually the 3mm material we used at the power generated full penetration. We had a lot of porosity actually detected after the XCT inspection. And on the 5mm, it was very clean. It doesn't matter what gas we use. So we had a bit of investigation because the 3mm material we used was cold rolled, and the 5mm we used was hot rolled. And we're still waiting for the XCT result from the lab to review the result of the 16mm, because 16mm also hot rolled. The question we had would be the manufacturing route actually influenced the generation of the porosity, or it was actually a surface condition. So there are still some trials going on in the lab, trying to remove the surface and re-weld using identical parameters on the 3mm just to compare the result. And yes, some future work. We are going to complete analysis on the 16mm welds, including their oxidation and XCT, and then we will have better idea to actually set up the direction for the next set of trials. And some initial feasibility trials, we tested the beam shape. That's definitely on our radar. We need to test it in the future, because some of the shape actually bridge the gap nicely. The gap, I mean, is the feet up. So considering a remote operation, putting two pieces of material together, probably it won't be ideal. We'd like to see what kind of beam shape and capability of the beam shape could give us the highest tolerance and also generate quality welds. Definitely, that will be the future trials. Yes, this is just a quick update from me. I wonder if anybody has any questions.
Thank you very much, Yao. So we have time for the final questions for Yao. So raise your hand and you can make your questions directly to her. I have a couple of questions. One is related with the beam inclination. Which options are you evaluating for the future?
Inclination, initially when we started, we set up at 6 because it's pretty safe. And I think a rule of thumb is we're not going to use something crazy like 30 degree, because it's not very sensible for a laser processes. Another why we want to test inclination is considering we have a really short standoff distance inside the pipe, and shooting a laser within a safe angle is very important, and understand the power delivery to the surface or to the material, and then to create a weld is very critical as well. I think we are aiming to see some range. To be fair, not 0, but in my mind, 0 to 10-ish, where we want to find a sweet spot. But I think 6 is pretty safe and is really good practice generally people use in the lab. But I have limited knowledge about what kind of inclination actually used in production, for example, like automotive or other industry. Yeah.
And are you going to combine with beam shape analysis, so controlling how is this inclination affects the beam shape? I don't know if you're doing this nowadays already.
We did. the initial tested, it was at a fixed. I think definitely because together with the shape and the angle, that will impact on the effective, how to say, power delivered into the material, isn't it? We would like to see the influence on that. If it's small influence, perfect. But if it's significant, that's definitely direction we need to work on.
Okay.
Yeah.
And I have another question regarding this study you mentioned for understanding the oxide thickness in the case of the nitrogen. Which kind of studies do you have in mind? Is kind of roughness of the surface or physical status of the surface, or is more kind of EDX to understand composition, potential components in the surface that you didn't consider at the beginning?
I think depending on how much we want to dig this rabbit hole, I think, for this project, the purpose is to identify the best combination of the parameters, including the shielding gases. And understanding a certain level of the causes is quite helpful. Probably some chemical analysis, then that can actually project or review what kind of like elements or things formed, and based on that we could know the potential of the cause of that oxidation. To me, that's a good level of understanding.
Yeah. Okay. Good.
Yeah.
Any other question for Yao or comment? Yeah, Jesus, final question. You need to unmute. You're muted now, Jesus.
Okay. Now, okay.
Now.
Question relating the measurement of sputters. Is okay? You measure the number of sputter and also the dimension on only the number.
It's the number per frame using the high-speed camera.
High-speed camera. Okay.
Yeah.
So it's a number per frame.
Yeah, it's a number per frame.
Okay. Interesting. Thank you.
That's okay. Thank you.
Any final question or comment? I think there is no more questions. So I think, well, first we thank you to Yao for the nice presentation and showing all these results. Thank you very much, Yao.
Thank you
For being here in the afternoon. And thank you to all the speakers that we have today. Sorry that we are a little bit later than expected, but we have some nice questions in between, so I didn't want to cut the discussions. Thank you, Pasquale, Klim, Christophe, and Yao for the presentation. Thank you to everybody for being here this afternoon. And as I put in the chat, we will put this video in our YouTube channel, Lasers4MaaS channel. We will have a next workshop in October. Probably more, we still need to define the topic, but probably we'll be focusing one of the use cases, so more dedicated and a part of covering also the advancement in the other work packages. So you will receive more information about that, and I hope to see you in future Lasers4MaaS events. So thank you, everybody. Thank you for being here, and good afternoon.